infrastructure at CERN, and our speaker will be Dan van der Ster from CERN. Dan manages the Ceph Storage service at CERN in Geneva, Switzerland. He has participated actively in the Ceph community for more than 5 years, being one of the first to demonstrate Ceph scalability up to multi-tens of petabytes. Dan has spoken at several Ceph days and OpenStack summits, acted as academic editor and the original Ceph advisor, and now has a role on the Ceph governing board. Dan earned a PhD in computer engineering at the University of Victoria, Canada in 2008. Ladies and gentlemen, please welcome Dan van der Ster from CERN for his presentation.
Hi, thanks for the invitation to speak at this workshop. I'm going to present the Ceph storage for our open infrastructure at CERN. So first, a little bit about CERN. This picture is showing the CERN Large Hadron Collider. So CERN is the largest particle collider in the world, located in Geneva in Switzerland. The Large Hadron Collider is a 27-kilometer underground ring, about 100 meters underground, and it uses superconducting magnets to accelerate and collide protons at just shy of the speed of light, so 11 kilometers per hour short of the speed of light, which is very fast, of course. This is a picture showing that underground tunnel and the blue superconducting magnets. And then this picture is showing the Atlas detector, which is one of the 4 large detectors at the LHC. You can see there's a person at the bottom of that picture, and basically this is a very large digital camera, and it takes pictures like this. This is a picture showing the Higgs boson, and the Higgs boson was predicted several decades ago, but then was observed in 2012 at the LHC. And this is the particle, the elementary particle that's responsible for mass. So that's an introduction of CERN. Now I get to our computing infrastructure. By quantity, CERN is mostly a high throughput physics analysis center. We use HT Condor as a batch system to manage our hundreds of thousands of CPUs. And we use a locally developed storage system called EOS to manage hundreds of petabytes of storage. And then we archive to tape using something called the CERN tape archive, hundreds of petabytes of tape. But in addition, and sort of behind all of this infrastructure, we are a large research lab with typical IT needs. And those IT infrastructure needs bring several low-level storage requirements. For example, block storage and filers for virtual machines and databases, object storage for web or cloud-native applications, scratch areas for our HPC and message passing clusters. And this is like the so-called open infrastructure. Here's a picture showing several of the technologies that we use. So, of course, at the bottom, you have OpenStack and Kubernetes, and then we use all sorts of open source software systems on top to build our infrastructure. We've used OpenStack at the base of this infrastructure since 2013, and it's presently providing around 90% of our computing resources. It's used for both physics computing, so that large-scale batch activity, but also our service infrastructure. So this brings a requirement on storage. What do we need for storage? We need something low cost, so we want enterprise features at commodity hardware prices. We need something compatible, so it should be well integrated with off-the-shelf open source software. We want modern high availability, so there should be no single points of failure. There should be no RAID. There should be failure domains, so we should be able to replicate things across different areas that might fail in the data centers. We want checksumming everywhere, and we want self-healing. We also need horizontal scalability. So if we want to add capacity or performance, we want to be able to do this just by adding more servers. And then when we look at above, we also want to have some software that has an active community with a positive future outlook. So here's an introduction to Ceph. Ceph is open source software-defined storage. It began as a research project back in around 2004, and then it went into a startup company called Inktank, which was acquired by Red Hat, which was then acquired, of course, by IBM. There are several different types of Ceph that you can get. And we use the Ceph Community Edition. But if you need enterprise support, this is available from Red Hat or SUSE or other consulting companies as well. The Ceph project is governed by the Ceph Foundation, which is a Linux Foundation project, and CERN is proudly one of the governing board members since the beginning. Ceph brings a unified storage platform. At the bottom, we have Rados, which is a reliable platform to build applications on top. And then Ceph comes bundled with 3 notable applications: an object store compatible with S3 and Swift, block storage for virtual machines, and an NFS-like file system, which is CephFS. And the magic of Ceph is something called Crush. Crush is what Ceph uses in order to do the following. So it can store data across failure domains. So you can describe your infrastructure, whether it's hosts or racks or rooms or data centers, to the cluster, and it will replicate accordingly. It does object replication or erasure coding. So for example, it's typical to have 3 replicas per object, or do 4+2 erasure coding if you want a RAID 6-like configuration. One of the nicest things about Ceph and Crush is that it enables fast parallel recovery when devices fail. So if a device is failing, then the degraded objects are usually re-replicated in under 30 minutes. And this is to compare with a typical old RAID array, which can take several hours or days to resilver if a device fails. Crush allows you to add or remove devices without downtime, and it enables minimal data rebalancing for cluster expansion or contraction. And it's also aware of device types. So you can have high performance pools with SSDs or NVMEs and store your bulk data on HDDs. Now I'll talk about Ceph at CERN. So our story began along with OpenStack at CERN in 2013. And we started with a 300 terabyte proof of concept, which we tried to did break, but eventually learned how to fix. And then we decided to go production. And we were production by Christmas of 2013. And this was with a 3 petabytes OpenStack cluster, 3 petabytes for OpenStack. In the following years, we helped build erasure coding and started using erasure coding and object striping in Ceph. In 2016, this was a notable event for us because we had a chance to replace all of our initial cluster with new hardware, and we did this without downtime. So this demonstrated that Ceph really can do what it promises. By 2017, we had 8 production clusters. By the last couple of years, we started doing more CephFS and S3 in production. And these days, we're just scaling out Ceph, adding more clusters, adding more use cases, and adding more capacity. Here's an incomplete snapshot of what we have in production right now. We have several clusters, 2 or 3 clusters of block storage for OpenStack. Some of these are hyperconverged, where we put hypervisors and Ceph on the same servers. We have several CephFS clusters. So we have one for the OpenStack and OpenShift use cases. And then we have a testing environment. And then we have an HPC CephFS cluster as well. We have a large S3 object storage cluster using erasure coding. And we have we have one large and one small Ceph cluster, which is used at the Rados level directly by our tape archive system. Now, it's important to say this. I said that this is an incomplete list because this year, and actually these days, we're renewing most of those clusters above, and we're also expanding, splitting clusters into several more. So this table in future presentations will probably be double in size. And in total, we have something like 30 petabytes now. Now to discuss the block storage experiences at CERN. So it's backing our OpenStack cloud. We have more than 4,000 virtual machine images and more than 6,000 attached volumes. One of the nice features is that Ceph and RBD does thin provisioning and does QoS throttles on the volumes. So thin provisioning means that we can offer 2 times the space than what we have in physical capacity, based on the fact that users don't usually fill their file systems. And then with the QEMU KVM QoS types and volume throttling, we enable 2 types of flavors right now: 200 IOPS for standard use cases and 1,000 IOPS for performance use cases. We have ongoing work to replace and expand this hardware, which is transparent for the end users. We've already expanded and replaced hardware several times by now. And this year, our typical server has dual Xeon CPUs, 192 gigs of RAM, 2 24-bay JBOD arrays with 12 terabyte drives. So this gives us, in one rack, it gives us 2.3 petabytes of storage. And since we don't want to put a dependency on one single rack, we usually then scale across 3 or 4 racks to make a approximately 10 petabyte cluster for our block storage, per block storage area, let's say. And something else that we're doing at the moment is we're testing an all-flash Ceph cluster to enable 2,000 and 5,000 IOPS volume types for our more performance-sensitive users. And in this case, the typical server is dual Xeon CPUs with 192 gigs of RAM and 16 2-terabyte SSDs. For S3 object storage, we started in 2015 for one of our physics experiments, the Atlas experiment, and they wanted to develop something they called the event service, which would, rather than storing large files as we typically do in high energy physics, large 1 gigabyte files approximately, they wanted to store small objects, so billions of 1 megabyte objects. We've been running this now in production for several years, and it works well for small scale event processing, where we have up to 1,000 concurrent jobs processing the data, or also storing logs files from those jobs processing data. However, our S3 infrastructure is not really large enough to do this at the full CERN and LHC scale, where we would need something like 10,000 jobs to put one of our entire compute clusters against this. So we would need to do some more investigations if this was going to be something that could scale up to the full CERN scale. However, in the IT environment, S3 usage is expanding quite a bit. We use it to back our GitLab repositories, where we have something like 50 or 60 terabytes of data in GitLab. Also CI build artifacts and container images. OpenShift is backed by this at CERN. And then also something called Boink, which is the LHC at home service, where users can donate their spare CPU cycles to help with the LHC processing. This is all backed by S3 at CERN. And something called CERN VM file system, which is a read-only global CDN of a fused file system. We back this on S3 as well. And one of the new use cases that we have for S3 at CERN is as backup. So we have a service called CERNbox, which is a sync and share solution for our users. And we're backing up roughly 20,000 CERNbox accounts to an S3 cluster. We do this with Restic, which is an open source tool you can find on GitHub. And this is efficiently taking snapshots of file systems, then deduplicating and also enabling incremental backups. And we find this to be very useful. Now onto CephFS. So we're currently operating 3 production CephFS clusters. We have a general purpose large CephFS managed by OpenStack Manila. Manila is used to export file shares to the users, and they can manage the keys to access the file system. We have roughly 250 of these shares for things like central physics services, Yum repositories, data center monitoring, again, OpenShift, and Kubernetes is backed by this CephFS. We also have a large CephFS backing our new email solutions. So we're building a new open source email solution. And for this, we have dedicated Ceph cluster nearby all of the infrastructure for that system. And then, as I mentioned before, we use hyperconverged CephFS for HPC. There we have 140 servers, and we have HT Condor running alongside Ceph on the same nodes. And then this is all this is an InfiniBand cluster, but Ceph is using the 10 gig Ethernet on those servers. Now, in the past years, we invested a lot of time to profile and tune CephFS for HPC, and we learned quite a bit about CephFS in this activity. So we had some investigations of the multi-MDS balancing. As Danny mentioned earlier, this works, but in fact, if you know your workload better, you can by manually pinning directories to individual MDSs, you can do much better. We learned about the importance of data locality. So the distance in hops from client to MDS to the actual disks and OSDs can have up to a 10 times performance impact on performance. And then we also investigated in something called lazy IO, which is an HPC flag that can be enabled on files or mounts to relax the data consistency. And this is useful in HPC applications, which are doing parallel IO to single files. When we were getting started with this, there was an effort at supercomputing conferences to kickstart something called the IO 500 benchmark. So this helped us focus our tuning efforts. IO 500 is a benchmark which is using IOR and MD test to benchmark a file system. So this slide here is showing us scaling up our metadata performance. So this is going from 3 to 10 active MDSs, and you can see when we enable the increased number of MDSs, the number of client requests that can be handled is increasing. So there was a bottleneck in the metadata before, and this unlocks the performance of the cluster. And this is CephFS on IO 500 with our initial results. So this was the first list. And in the first list, okay, we have a very small cluster for HPC, and we were number 36 on the list. We also have done in the past some very large scalability testing of Ceph. Each time that we get a new delivery of hardware to CERN, we can have the opportunity to borrow that hardware and run big Ceph tests. So the first of these tests was a 7,200 OSD test, 30 petabytes in total. This was back in the Ceph Hammer days, maybe 5 years ago. And there we found several limitations distributing OSD maps across the cluster, which led to some optimizations. In our second cluster, we found, again, limitations in messaging between OSDs and MONs. And this was part of the motivation for Ceph to add a daemon called the Ceph MGR. Our third large-scale test was a 65 petabyte test with more than 10,000 OSDs. And this was actually just before Luminous. And it proved that all of the scalability improvements that were included before basically worked. And there were no large operational problems with a cluster that size. Something recent that happened to us, I call this our bug of the year. In February of this year, we suffered a several-hour outage on our large block storage cluster for OpenStack. The details of this were described in a Ceph Tech Talk, which you can find on YouTube. And spoiler alert, the root cause of this was found to be a bug in the LZ4 compression library. But this bug basically made us reevaluate our Ceph strategy, because even though the likelihood of a Ceph outage is quite low, we have had several years of uptime with no incidents. We found that then the impact of an outage is very high because a lot of services build a critical dependency on the Ceph cluster. So we asked ourselves, what's better, one big reliable cluster or several smaller clusters? And we decided to move in the direction of several smaller clusters. This way, the impact of an outage will be minimized and very critical services can span several clusters. So this year we've been procuring more hardware, splitting into several clusters, and our users currently have to manually select volumes on specific clusters, but we want to make this kind of cluster scheduling more automated in the future. Some other ongoing projects that we have include, I mentioned earlier CERN Box. This is our sync and share solution for documents, also data analysis, and general as a collaboration platform. And something that's unique about our CERN box is it allows this sync and share and access on the web and on your laptop, but it also allows direct access via Fuse to the files from our large-scale computing systems and batch systems. So one project that we have ongoing is to evaluate if CephFS could be used as a backend for this type of service. For a sync and share service, you need two features, basically. You need in your file system a way to keep recursive statistics to know if a file somewhere deep in your hierarchy, in your file hierarchy, if some file has changed, so you don't have to stat every file of the system. But you also need file versions. Now, CephFS has both of these features, so it's a good candidate for this to work, and we're evaluating the details if we can make this work or not. And the second thing that we have ongoing is CephFS, as people know, requires you to have nodes on the same storage network, basically. But our lab relies a lot on Kerberos for secure access to data. So we're testing at scale how to use NFS Ganesha to act as a highly available Kerberized access to our CephFS clusters. And the initial use case is for remote access to our HPC home directories and scratch areas. Now some concluding remarks. So these are my general impressions. Ceph is very reliable, so it makes hardware failures basically transparent, and the users are almost never served inconsistent data. We have, I can't think of cases where we do check summing on top of Ceph even, and I can't think of cases where we had inconsistent data served to the users. On the other hand, Ceph has been historically a challenge to operate. You need highly skilled sysadmins, especially at the time that you're architecting or designing your clusters. But this is getting much better recently in recent versions of Ceph. Performance-wise, Ceph largely depends on your hardware. So Ceph is consistency first, performance second. It's flushing buffers for power loss safety all the time. So if you need high performance, you really need good SSDs or NVMEs for high performance deployment. One of the best features of Ceph is the community. The Ceph community is very friendly and helpful. So we have lived so far without commercial support. But in exchange for this, we try to maintain a good community karma on the mailing list and participating in events like this one. Now, lastly, one of the main nice features of Ceph is that it's usually early in being compatible with emerging IT technologies. The Ceph developers upstream actively participate and shape the different open infrastructure trends. So Ceph is the de facto OpenStack storage backend, and it now backs a large number of the Kubernetes deployments. And you can bet that if there's another new open infrastructure technology coming out, Ceph will be able to serve as the storage backend for that technology. In summary, I can say that Ceph, the open source storage system, is backing our cloud, container, and HPC activities with block storage, object storage, and distributed network file systems. We have more than 7 years of experience, and it's been proven to be a stable, reliable storage for our open infrastructure. Its features and its integrations make it attractive, and the friendly community and good industry alliances also show its future. So then you can, of course, find more at ceph.io. And that's the end of my talk, so I'll be happy to answer any questions.
Okay, Dan, thank you very much for your presentation. We have a question about your workloads. Where do you prefer using replication, and what kind of workloads you prefer erasure coding for?
Okay, that's a nice question. So we use replication. First of all, we use replication on our clusters, our long-lived clusters, because those were deployed and have been upgraded since before erasure coding even existed as a feature in Ceph. We primarily use erasure coding. We use erasure coding for object storage. So for our S3, the data is stored erasure coded because it's not it's not so latency sensitive like block storage. We also use erasure coding for our large Rados only clusters that we use to back our tape system. And then the new use case where we're using erasure coding is on our all-flash clusters, which is maybe unexpected. But our bet is that with all flash, so SSDs being more expensive, we can decrease the cost by using erasure coding there, and thereby get all flash performance at not much of a price premium over HDDs.
I have a personal question. How do you decide the maximum number of disks in an OSD node, considering the environmental factors like the total number of OSD nodes, network capacity, and the others?
Yeah, so at CERN, we usually don't have the luxury of specifying exactly which type of hardware that we want, taking only Ceph considerations into mind, because each year we buy maybe between 60 to 100 petabytes of storage, and most of that by volume goes to our physics storage system, EOS. So what we do, I mean, the Ceph number of nodes, number of OSDs per node, of course, is dominated by the memory considerations. But what we found in, say, the recent versions of Ceph, by recent I mean last, say, 2 years, is that you can squeeze a lot of OSDs onto a single node with limited memory. We have so most of our machines, our older machines, have 24 OSDs with only 64 gigs of RAM, and this is working well. The OSDs stay under that memory, like they fit within 64 gigs, no problem. We have some machines with 30 HDDs and only 64 gigs of RAM. But in that case, we think it's a little bit too tight to run 30 OSDs. So we stripe those HDDs to make, with LVM, to make like a RAID 0, 15 RAID 0s, and then we run 15 OSDs.
Mm-hmm. Do you prefer to use any JBODs, and do you share JBODs between the nodes, OSD nodes?
So the typical hardware that CERN buys is, so one rack will be made up of a 3U server quad with 4 servers in a 3U unit, and then we attach to that JBODs, so we can fit 8 JBODs into one rack, 8 24-disk JBODs, and that composes. When we acquire that today, this is 2.2 petabytes in one rack.
Okay, thank you. I think we don't have any other question, and thank you very much for your presentation. It was very useful and a great presentation. Thank you very much for joining us. Okay.